is one of those where we are going to write the limit definition for the area under the curve. So the function that we've been given here in problem 16 is that f of x is equal to, no, I'm looking at the wrong one, x squared plus the square root of 1 plus 2x. And we've been told that x is between 4 and 7. Well, the good news on this problem, and this is consistent with what Chaudhuri said his expectation on the short test is, that we're not going to have to evaluate this limit. And as I mentioned last time, for almost every function, we actually don't know how to evaluate that limit anyway with our 17b skills. So we've just been asked to write an expression for the area under the graph using a limit. So this first part is the same every time I'm writing it. I'm always going to have the limit as n approaches infinity and the sum from I equals 1 to n. Partial credit just for writing that, maybe, I don't know. I bet you'll get partial credit just for writing that. So that's the same each time. The two pieces that we have to actually apply the specifics of the problem to are to figure out what our delta x is, and then to find our f of x sub I. And again, Chaudhuri's told us we're only going to worry about right-hand endpoints. So that's the one that we're going to use when we find that x sub I. So the first thing I want is my delta x. And that delta x is going to come from 7 minus 4 over n. Or I'm going to write that as 3 over n. The next piece that we need is our formula for the x sub I. And again, we're going to use the formula for the right-hand endpoints. So my x sub I, the generic formula looks like a plus I delta x. So for us specifically, a is that starting point. So it's going to be 4 plus I times 3 over n. Now we're just going to put it all together. So I'm going to have the limit as n approaches infinity of the sum from I equals 1 to n, or delta x is 3 over n. And f of x sub I says, take this whole kind of messy looking thing and plug it in everywhere we have an x in the problem. We're not going to do anything with it. We're just going to plug it in. So where we've got that x squared, we're going to end up with 4 plus 3i over n squared plus the square root of 1 plus 2 times, and now I'm plugging the whole thing in for x again, 4 plus 3i over n. Walk away. At least in terms of the exam, we're done. Don't try to simplify that. Just walk away. I'll give you a second in case you're trying to copy that down on your paper. That's my f of x. So I want to talk about notation a little bit and some of the signed area sorts of questions that we might be asked. So I'm going to give us some sample questions here. So my first sample question is to evaluate the definite integral from -3 to 0 of f of x dx. So this is asking me to find the area from x equals -3 to x equals 0 that's trapped between our function and the x-axis. Now from -3 to 0 in terms of x values, all of this is below the axis. So already I know that my answer to this question is going to be negative. And that's the idea of signed area. So if the area is below the axis, then we're going to get a negative value. The next piece of this is that's a triangle. And if it's a triangle, we should be able to evaluate this using our geometry knowledge. So I know that looking at this, if I've got a triangle that's going to be 1/2 the base times the height. Well, the base here is 3, and my height is 1.5. So that's my interpretation for signed area for that integral. Now, suppose that I wanted to find the definite integral from -3 to 5 of f of x dx. I think that this might play into the question about formulas around definite integrals. So one of the things that we can do, because we can see what's happening on the graph here, is this area from -3 to 5 of f of x dx, I can actually think about as multiple pieces. So when I look at this picture, especially if I'm doing it with geometry, I might visually see that I have this triangle, this bigger triangle going from -3 to 3, and then a rectangle going from 3 to 5. So one of the things that we can do with definite integrals is to break this up and say, well, this going from -3 to 5 is equivalent to taking the area from -3 to 3 of f of x dx and adding that to the area from 3 to 5. I don't really think about it as a separate formula. I personally think about it visually. So that total area is the same whether I do it as a triangle plus that rectangle, or if I treat the whole thing as a trapezoid. I'm going for the triangle plus the rectangle. So this area from -3 to 3 is that larger red triangle. So I know I'm looking at 1/2. The base of that triangle goes from -3 all the way to 5. So that's 3 and 5 more. So that's a base of 8. And my height here is -3. Now on the previous example, I said we're below the axis, so I went ahead and took care of that negative sign. You could also just recognize that the height has a value of -3 and plug in a -3 here. Either way works, as long as our overall response to that area, we make sure to preserve the minus sign. For this next piece, for that rectangle, I know I'm looking at a base times a height. Well, the base of that rectangle is 2, and the height is -3. So I'd have 2 times -3. There are a couple of things about definite integrals that are more formula-like. So one example of that would be if I asked us to find the definite integral from 6.5 to 5 of f of x dx. This is more of a mathematical convention than anything else. But this is asking me to find the area from 6.5 to 5. So it's asking me to find the area of this triangle. But here's the formula part. in English, we read from left to right. And when we talk about like a number line or our x-axis, our values increase as we move to the right. Because we read the integral as going from 6.5 to 5, this notation-wise is telling me that I'm going backward. So one of those actual formulas that we do need to know around integrals is that this is equivalent to doing the negative of 5 to 6.5 of f of x dx. So if you switch the order of the limits, we make the whole thing negative. And if we think about that in terms of like x and y values, essentially going from 6.5 to 5, we would call that a base of negative 1.5 because we went backwards. So this would become negative, and then I'd find that area. And because the area is below the axis, my y values are negative. So I'd have 1/2 times the base of 1.5 times the height of negative 3. So if I'm going to find the area in here, I'm going to use that area of a trapezoid formula and say evaluating this integral is the same as finding this area in here and finding that area in there would look like, well, my base is 4. I think I'm doing the math right this time. So my base is 4. And then I'm going to multiply that by the average of the two heights. So now I need to figure out what was the height when we plug in 1. Well, if I plug in 1 for x, I'll have 2 plus 1/2. Yeah, we could do that as decimals or fractions. 2 plus 1/2 is 5/2. And then my height at 5, when I plug in 5, I'll have 5/2 plus 2 sounds like 9/2. And then walk away. So if I found the area of this shaded region and I wanted to write that as a definite integral, then this would look like the definite integral from 1 to 5 of f of t dt. And if I changed this from a 1 and I called that saying that I was going from a to 5, then this wouldn't be a 1 down here anymore. It would be some kind of a. And now here's the part where I'm going to ask you to make a leap of faith. I claim that this area depends on what number we put here, right? If I'm going from a to 5, that's a different area than if I was going from a to 6. So I'm going to define a new function. And my function is going to be a function of x, where x is telling me I'm going to take my integral from a over to x. So this thing right here, which is the area of the shaded region, is a function of x. If I tell you what x is, you can find the area. And now comes the fundamental theorem of calculus part. What if I didn't want to find the area to x? What if instead, pretend I'm going to draw exactly the same picture. It's going to be perfect. What if I didn't want to get the area from a to x? But what I actually wanted was some little skinny area out here. And if that's my x value, and I'm going to scoot over just a tiny bit, I'm going to call this x plus h. Now, if the little light bulbs are going off in your head going, wait, x plus h, that's suspicious. That sounds a lot like stuff we did in 17a. The worlds are about to collide. We're bringing it all back together. So I want to find that area in there. And as a function, now that I have this convenient notation up here, I know that that area that I want, I could get by thinking about the entire area from A over here to x plus h. Sorry, that glare is really bad. The entire area from A over to x plus h, and then subtract off the area in there. So to get the area of this shaded region, I'll just draw it, right? To get this area, that would look like f of x plus h minus f of x. Next step, we're going to do the lazy mathematician thing. Also, you all probably didn't notice, but it did stand out to me that Chatteray also said mathematicians were lazy. Must be a trend. So we're going to do the lazy mathematician thing, which is, yeah, but I don't really know what that function is. So let's just pretend that's a rectangle. And if we do that, and we pretend that that thing is a rectangle, then if I cut this off right here, and here's my, and instead of finding this thing, we just find the area of this lovely rectangle right here. It won't be equal. It won't be exactly the same, but the area of my orange rectangle will be almost the same. And if I find the area of my orange rectangle, since it's a rectangle, I can do base times height. Well, my base here is the distance from x to x plus h, or just an h. And the height of my rectangle, as I've drawn it in, I'm going to find the height at a value of x. And remember up here, this was the function little f of t. So my height here, or like the coordinate at that point, is x comma little f of x. So the area of my orange rectangle is a base of h times the height of little f of x. And that's almost equal to the area I really wanted. And now you might look at that and say, huh, well, I suppose we could divide both sides by h. And then do the thing that we did a lot of in 17a, which is take the limit as h approaches 0. And if we take the limit as h approaches 0, and I didn't leave myself a ton of room here, but I'm going to squeeze in a limit as h approaches 0. This will actually become f of x. And as you all might notice, this thing over here is somebody's derivative. So little f of x is equal to the derivative of our big f of x. And that right there is 1/2 of the fundamental theorem of calculus. Now there's a question about why the f of x plus h minus f of x. And I was kind of going through this and erasing my pictures as I went. But the thing that I was originally trying to figure out isn't the area in here from a to x, but what I actually was looking for is this piece of area right here. So to get that piece of area, that's where I had to do the a to x plus h minus the a to x. Yes, this is the limit definition to get a derivative the long way, for sure. So all of that really was just to get to this thrilling conclusion right here. You will not have to do any of that on the test on Wednesday. The thing we do need to know is this right here. So let's go ahead and start using it to see really what we're doing with that fundamental theorem of calculus. Okay. I'm about to erase stuff, so I'm trying to pause. Just give another second or two for the questions to show up. Again, I've got a handout that kind of walks through those steps for you. Yes, so f of x is, we have an antiderivative relationship, correct. Did we do anything with the red shaded area? No. My red shaded area was just to show off that we were taking the whole thing minus the red part to get the skinny piece. I'm going here next, so hold off on that for a second. Not seeing any more questions pop up. Let's do some examples of the kinds of things we actually need to finish the homework assignment and web work and to be ready for the exam on Wednesday. F of t is the height. F of x is the height at x. And again, this is all just to derive the formula. Let's do some actual problems and we'll see if that clears up some questions. Now there are two parts to the fundamental theorem of calculus, and I do have a proof of the second part of it in the notes in Canvas, and I'm sure that you're going to see it in lecture today. So I'm not going to worry about that second part. Please just for the moment, believe me on this. What this really is telling us is that when we write this notation of an integral and we have some function in here, that function is somebody's derivative. So the answer to the integral is the antiderivative of whatever was in here. So this is equal to finding that antiderivative of f of x. That's the whole point of the fundamental theorem of calculus. It says we can find the area under the curve by finding the antiderivative of that function, and then the second part, plugging in the endpoints. So let's do some examples because I see there are a whole lot of questions. So as an example, that's part one of the fundamental theorem of calculus. I said there were two parts. The second part says, if I'm going from A to B of f of x dx. To get that area, this is equal to the antiderivative function evaluated at b minus the antiderivative function evaluated at a. That's the second part of the fundamental theorem of calculus. Let's do some examples, and I promise it'll get better. So, oh, well, let's do that one that we had with the trapezoid thing, right? Someone's gonna have to remind me. We were going from 1 to 5, and the function was 1/2 x plus 2. I think that's the function we had before. Cool. So what those fundamental theorems of calculus say is they're giving us a two-step process for evaluating this. And I guess I have to stay over here to keep blocking the glare. Step 1, find the antiderivative. And then step 2, plug in the endpoints. So let's start by finding the antiderivative. Well, this is using our section 4.6 skills. So if I need to find the antiderivative of 1/2 of x, we're going to add 1 to the exponent and divide by the new exponent. So this will turn into x squared divided by 4. And again, I'm getting the 4 because I already had a 2 in the denominator. And then I have to also divide by the new exponent. When we take the antiderivative of 2, there isn't an x on the back of that, or we can think about it as an x to the 0. But the antiderivative of a constant is that we're going to get that constant times x back. That's step 1. Step 2, in evaluating the definite integral, we're going to plug in the endpoints. And the notation that we use here, because we've already found the antiderivative, the notation that we use is a vertical line. And then we put those limits on here, a 1 and a 5. Step 2 says I'm going to plug in the b limit and subtract off plugging in the a. So this would look like 5 squared over 4 plus 2 times 5. That's me plugging in the 5 minus me plugging in the 1. 1 squared over 4 plus 2 times 1. And that would be my final answer. Now, does that look anything like the other thing that we did? No, but if you take a minute numerically, they will work out to be the same number. Okay, a couple of questions. Did I multiply the 2 by 2 on the bottom? Absolutely, that's how I got 4. Would I include the plus c? Nah, though there's a subtlety there. I'm not including the plus c on the antiderivative because I have endpoints. So don't take notes for a second. I'm going to show you what would happen if we did the plus c. So don't take notes because it's not what we would actually do. I'm just showing you what would happen. You would not do this. You should not write this. Don't take notes. Let's say that I found that antiderivative and I put a plus c on there because we were finding the antiderivative. But then that second part of the fundamental theorem of calculus told us that we were going to plug in the 5 and subtract off plugging in the 1. And notation-wise, we rate that as a 1 and a 5. And if I did that, I'd have, I'm going to write it pretty fast here, but I'd have 5 squared over 4 plus 2 times 5 plus c. And then I would subtract off 1 squared over 4 plus 2 times 1 plus c. And when you do the subtraction, the c's go away. So the thing to remember is that if I have an indefinite integral, that's what we call it when we don't have bounds. If I have an indefinite integral, then your answer is going to be that antiderivative of f of x plus c. But when we have a definite integral and we have bounds, then my answer is going to be this two-step process. Find the antiderivative and then plug in the endpoints. And I promise we will get more practice with this on Monday. If you wrote the plus c and it was a definite integral problem, you would probably have points taken off for the problem. That is an excellent question around what would the instructions say. So let me actually pull up. Sorry, I was trying to grab the textbook. So these are like the 5.3 questions. And 5.3 is on the exam. And the really unexciting directions in section 5.3 say things like evaluate. Ta-da, we evaluated. So I told you not to take notes on this because that is not what you should write. If you have limits of integration, meaning like if you have a lower and upper bound, you should just get a number at the end. There should not be a plus c. If I asked you to find the general antiderivative for something, like let's say I just asked you to find the integral of cosine of x dx. These instructions say find the antiderivative for cosine. And the function whose derivative is cosine is sine. Here, because it's not a definite integral, I don't have limits. We're not talking about it specifically as an area. We're going to include the plus c. This guy's we call this an indefinite integral. This one we call a definite integral. And we'll kind of spend the rest of chapter 5 getting more practice around these.